Welcome to the first video in our gas chemistry series. In this video, we'll look at the four most important variables to look at when predicting gas behavior, as well as look at a bunch of assumptions that we need to make about how gases behave in order for us to study them in chemistry. The first variable that we can talk about is gas pressure. So gases are unusual compared to liquids and solids because they don't have a constant volume or a constant shape for a given mass of gas particles, unlike liquids and solids. So one of the ways that we can measure gases quantitatively is by looking at gas pressure, which is the force that is exerted outward by a group of gas molecules as they move and occupy a specific volume in space. We can also measure gas volume because of its direct relationship with pressure. So gas volume is the 3D space that gas particles occupy, and normally gases will migrate outward away from each other and fill up the entire volume of a container unless a force, dare I say, a pressure from outside is exerted on the gas molecules, thereby restricting the 3D space in which they can move. Next, we have temperature, which is obviously going to affect the movement of gas particles. Temperature is simply a measure of how much kinetic energy, that being the energy due to movement, a group of particles have. So a higher temperature means that gas particles are going to be moving faster, meaning that increasing temperature means that gas particles have more kinetic energy, and if they're moving faster, they will likely expand outward and occupy a greater volume. And the final variable we know very well, it's the number of moles. Obviously, the greater the number of moles of gas particles are, the higher the pressure is going to be of that gas, and the more space that gas will occupy, assuming that the gases can expand outward in every direction. We will focus on those specific relationships between these four variables in the subsequent videos. For now, let's take a look at some assumptions that we need to make about gases. Assumption number one states that all gases are to behave identically under experimental conditions. Now, what this means is that it doesn't matter what the gas that we're looking at. It can be a very reactive gas like hydrogen and oxygen. It can be a completely unreactive gas like our noble gases, helium, neon, argon, and xenon. It doesn't matter. The behavior of all of these gases based on temperature, pressure, volume, and the number of moles is going to be identical. Assumption number two is that gas particles only behave or only move in straight paths, which means that we don't get curved motion like we see in the diagram on the left. And this assumption is tied into assumption number four, which states that no attractive or repulsive forces exist between gas molecules. And this is very important. Let's say that we're dealing with a gas that is polar, or dispersion forces that exist within gases. If we get a negative pole on this gas here, and this gas has a positive pole here, that will influence the direction of gas path travel. So the assumption about no significant attractive or repulsive forces also means that because these dipoles are not here, that there is no attraction or repulsion that would stop gases from moving in straight paths. And number three relates to how gases collide. So when gas particles hit each other, the assumption is that all collisions are going to be 100% elastic. Now, what this means is that when all gas particles move, they have a certain amount of kinetic energy, and an elastic collision assumes that the kinetic energy transfer that occurs from one gas particle to another are 100% efficient, and none of this energy is lost due to heat. Now, these sound like pretty big assumptions, but we make these for a good reason. We make these because we consider gases, or we do most of our research and experimentation of gases at what we call standard atmospheric temperature and pressure, or SATP for short. And atmospheric pressure, which is what we label as 1 atm, or 101.3 kilopascals, and atmospheric temperature is what we consider 25 degrees Celsius, or if you convert to the Kelvin scale, 298 degrees Kelvin. Now, at these conditions here, most gases behave like what we call ideal gases, which are gases that follow these four requirements here. There is another trend that we can observe related to these four assumptions and the behavior of gas pertaining to temperature. If we consider gases at high temperature and low pressure, which means that there is a minimal force exerted outside the gases and they have a very high temperature, which means they're going to be moving very quickly and they're going to have a very high amount of kinetic energy. Now, if there is a very low pressure, there is minimal force to keep the gas molecules from coming close together, which means that any intermolecular forces that occur are basically going to be non-existent because the gas particles are very far from each other, and because they're moving very quickly, they're just going to keep moving really far away. So at high temperature and low pressure conditions, gases behave more like ideal gases, i.e. gases with these four assumptions, because the intermolecular forces are very weak because the gas particles are very, very far away from each other. However, if we decrease the temperature, which means that gas particles are moving very slowly, and if we increase the pressure to force gas molecules to come close together, the gases will behave like what we call real gases. And a real gas is a gas in which these four assumptions are no longer true, because as the gas particles get closer together, that means that all of their intermolecular forces, especially dispersion forces, are going to get stronger, and therefore gases are no longer going to follow these assumptions here. In the next videos, we're going to look at direct relationships between pressure, volume, temperature, and the number of moles that will allow us to derive a formula that we can use in gas calculations.